Hello, I'm Howard Reeder, a founding director of Mesa Solutions, and I'm presenting this video technical note on seeing electromagnetic compatibility with different eyes. EMC is difficult to understand, and we'd like to make it easier. How do I see electromagnetics now? When I was a young person, I was intrigued by how signals propagated. I did electrical engineering to understand this better. This helped greatly, but my perspectives remained way off. I then did a doctorate in antennas and time domain electromagnetics, but the picture was still forming. I then became an academic, lectured for a long time, and I've been on a journey which I now gladly share. Please consider this picture of a NASA probe on the far side of the moon, looking from the moon to the Earth, and you'll see that the moon in this perspective is quite large. It's in fact, in capacitance terms, about 7 or 8 capacitance microfarads large. It's a big blob in our universe. I now draw a picture which has got some houses, and I'm going to ask you the question, what do you see? This picture was presented to me first by Piet van der Laan at the Eindhoven University of Technology and his colleague Lex van Dersen, and I acknowledge them gratefully. The picture here is of a Dutch house where rain on the roof is easily handled. And this rain is like electric field, and you can easily short it out with metal plates. What happens, however, is that this rain or electric charge can fall off onto the ground, and if it goes into rivers, which then run through the house, it can be catastrophic. So what they do in the Netherlands is they place the water into canals off to one side and divert the energy away from the problem. That is a metaphor. You look on the right-hand side here, slightly bigger metaphor. What do you see there? This could be clouds in the sky, and if a lightning strike occurs, the lightning current doesn't just disappear into the ground and that's it. It's not a sewer. There has to be some kind of closure, and this is this capacitance showing here, where currents and charge equilibrium takes place in circles. It could, however, also be circuit boards connected together, or it could be systems connected together. Currents always flow in closed paths. Further perspectives that made a big difference in my electromagnetics came from Dr. Dave Geary, who's given me a lot of his wisdom, which he derived from Carl Baum, with work that they started in the 1960s on lightning and electromagnetic interference. I also wish to thank colleagues and students at Stellenbosch University for some of the experiments you're going to be seeing. So what is key in this field? We use the same approach in EMC for all systems, whether they're small or large. To illustrate this, we're going to show you some basic building blocks. We'll start on a large scale and then zoom in. And the principles apply to both low and high power, and also low and high frequency. Electromagnetic compatibility, EMC, incorporates both the interference part, that stuff which you produce comes out, and then the susceptibility part, EMS, which is where anybody else producing a legitimate amount of energy comes into your system, stops it working, and you become vulnerable. You're then susceptible. And EMC has got both those two parts. The key focus here is to identify troublesome currents and divert them. Now I'm going to hand you over to some video material I prepared for Omicron in Austria, and I acknowledge him with thanks. And this is going to illustrate these points for a wide audience. For me, I need a reference framework. And what I want to do is just give this reference framework, which gets expanded on in the more detailed material, calling this an aid memoir, something to help me remember things. The first picture here, top left, is an indication of a wire coming out of the page. And the wire coming out of a page produces magnetic field going around it. And we use the term H field here. And the H field is in amps per meter. And if we sum up all the amps per meter magnetic field, it'll sum up to the current which creates it. So the current causes a magnetic field circulating around in this right-hand direction, and those two things are fully compatible. The picture in the middle is the same picture. It's called the right-hand rule, but this time you'll see the current creates a B field, and the B field and H field are identical, except that the B field also incorporates the medium magnetic material mu. So B and H people use interchangeably, but B has got more to do with the magnetic environment in which you're working, and it also shows you that current in a direction causes a magnetic field circulating around it. And if you put that current into a coil on a core, The direction of the current is where your fingers go, and then the magnetic field coming out of that coil will point in the direction you see to the right-hand side. This just helps us to identify in which directions magnetic fields flow because of current. That is known as Ampere's right-hand rule. Another really important boundary condition is that if you know in which direction the magnetic fields are flowing, you can then work out the currents that are created as a consequence of that magnetic field. Or if you put currents onto a metallic structure, for example, if you know the direction of the currents, what this boundary condition tells us, and it's not something that we created for fun, it's part of our universe. It's a physics boundary condition, which is a part of why our system is stable. What that observation tells us is, if you know the current and you know the normal, that's the vector pointing away at right angles, that the magnetic field is always at right angles. So the magnetic field, the normal and the current are always at right angles to each other, and that boundary condition helps us to find currents. That'll be an important theme. If you induce currents or fields onto a particular structure, like this box, or if you can imagine this wall being metal, if I put a field onto that wall, how far does it penetrate into the wall? We use a concept called skin depth. And skin depth relates us to 4 pi, a constant you're familiar with, the frequency of operation in hertz, the magnetic medium, that's mu, and then the conductivity of the medium, sigma. And if you put in the right parameters, for example, for seawater at 1 kilohertz, you'll discover that a wave penetrates to 1 skin depth, which is about 67% of its value at the surface. It penetrates 1 skin depth, which is 8.76 meters. And that is helpful to know because seawater, which is conductive with salt, a typical wave at 1 kilohertz will go in about 10, 12, 14, 15 meters into that seawater. If you take an aluminium box like this box over here, the penetration at 1 kilohertz is only 2 millimeters. This will be helpful for us, as you will see. So let's talk about shielding boxes. So now I'm going to bring the shielding box a little bit closer to you. It's a shielding box which is deliberately not square, it's rectangular. The picture that you see is of a square metal box, and in that metal aluminium box I'm going to put 3 coils, and these 3 coils are at right angles to each other. And to try and cause energy to get into this box, we're going to use what is called Helmholtz coils. Slightly better picture of the Helmholtz coils can be seen with where my cursor is right now. If you put current into those Helmholtz coils, the current, because of the right-hand rule, will generate a magnetic field, and I'll use the cursor to illustrate this. It'll generate a magnetic field which goes across the surface, across the face of this box. And the moment it goes across the face of that box, it touches metal, and because of that Ampere's right-hand rule, it causes currents to flow. And it turns out that if you've got a box with Helmholtz coils causing magnetic field, the right-hand rule tells us that it creates currents which go in the opposite direction to the currents which created it in the Helmholtz coil. That's very nice for us to know, because currents in the Helmholtz coil will cause opposite currents in the same direction in the box, which is great. If I take the lid off the box, what do the currents do? They start to go into the box, go to the bottom, come up the other side, and they rotate around the box. And in that process, they pull the magnetic fields down into the box, and in pulling the magnetic fields down into the box, they will intersect with coil Y or coil X or coil Z. This is not something everybody would see immediately. So a very simple experiment is the one that you see in a laboratory, just a simple oscilloscope, a simple signal generator. And what you can see here on the oscilloscope screen is that there's a sinusoidal signal being measured by one of those coils. And I can check, is it on the X coil, the Y coil, or the Z coil? And I can turn my box around through different orientations to see the effect of doing that. Sadly, these aluminium boxes, if they're untreated, grow an oxide at about a nanomillimeter per day. It grows more slowly afterwards, and the oxide that it creates is an insulating layer. So what you might do is you might build some electronics, you clean the aluminium up, you put the electronics in the box, you seal the box up nicely like this. Currents flow on the outside of the box because they can't get in because there's nice conductivity. But a day later, you discover that the box is not shielding things so well. And that's because oxide's beginning to grow. And currents, like water, will always get in through gaps. The currents get in through the gaps, excite fields in the box, and this causes coupling to the inside of the box, which is electromagnetic susceptibility, or comes out of the box, which is electromagnetic interference. The experiment which is implied here is a fun experiment to do, and most people after doing the experiment find that they understand how these currents and fields cause penetration into a box or out of a box. I'm going to expand this aid memoir, things I need to remember when I'm doing work in electromagnetic compatibility. I've explained here in the top left the Ampere's law, and I've tried to give an illustration of it. The equations on the right are quite famous equations, Maxwell's equations, and to be honest, for many people, even if they study them, it's quite intimidating. So what I'm going to do is I'm going to give you a verbal description just of the last two equations. This little curl, or in German rot, the curl tells me something happening in a certain orientation, in this case circulating electric field, is as a consequence of something happening at right angles. That cross indicates right angles, and this curl or rot indicates rotation. Something rotating in a certain orientation causes another response. In this case, the rate of change of magnetic field causes electric field. This is very helpful for us because it allows us to explain how waves propagate from your cell phone out to another cell phone. The currents go onto the antenna, they create electric and magnetic fields. The magnetic field creates an electric field, creating magnetic field at right angles, and that explains how waves can propagate. So it's quite useful to have that, and it's also helpful for us to know the orientation. This law says that if, for example, you've created the electric field because of a varying magnetic field, the electric field, which is linked to this term D, the rate of change of that electric field causes the rate of change of magnetic field, and that closes the equations in terms of propagation. I've gone through that quite quickly, but it's a three-dimensional explanation noted by Maxwell, telling us how waves propagate in space and how they couple into media. The loop underneath here, Lenz's law, is also quite interesting. If you have a loop of wire, so you've got an experiment and you create a loop of wire, if there's any magnetic field which cuts that wire, it will cause an induced voltage which causes current to flow in the loop which tries to oppose the field which creates it. Now, this reaction law is very helpful for us to know because we can use that to predict the direction of currents on devices like boxes like this or cables on these boxes, which allow us then to move the currents away from our problem and help to solve EMC problems. That's called Lenz's law. This little civil expression might seem to be unusual. What I could show you in more detail is that if you have a d by d term, which is a d by dt term, rate of change, like rate of change of magnetic field, if you go to a single frequency, that d by dt is very quickly shown to be equivalent to j omega. And j in our engineering system, mathematics and engineering, tells us something's gone at 90 degrees. And what civil tells us is that if you have got a signal, which you see on an oscilloscope, and if you notice that the current comes before the voltage, the coupling in that circuit is capacitive coupling. If you notice in a particular loop or something you're trying to protect, that the voltage signal comes first and the current signal comes afterwards, then you've got an inductor. So where the voltage comes first and the current comes second, this tells us that it's inductive coupling, and if the current comes first and the voltage comes second, it's capacitive coupling. And I just remember civil, and I would describe that in more detail. In the more detailed evaluation of things, there's a fun experiment on field distributions. This is a box, which is a microwave oven here in the middle, and you can imagine it just being a bigger box. Remember my principle, everything scales. This is a bigger box, and if we had the time, I would bring a microwave oven here, I would put a glass of water in the microwave oven, I would switch the microwave oven on, and I would show you how LED bulbs go on and off, or neon bulbs go on and off, according to the field distribution in the microwave oven. And to some extent, this has been illustrated in these pictures here, which come out of a book that I wrote together with a postdoctoral colleague, Patrick Chan, in 2000. And what we did was we put a microwave oven, we put a dielectric into the microwave oven. We drilled some holes, very small holes into the microwave oven, so we could look in using an electric field probe. And we measured and computed, showed them to be the same, distributions of energy with different loads. If you don't have a load in the oven, as illustrated in this bottom left picture, what happens is in the microwave oven, you get these fields which vary very symmetrically, like violin strings being plucked in all three dimensions. The moment you put a load in, though, and that's illustrated by this little load down here in the corner, the moment you put a load in, the field distribution changes. And if you can visualize these things, it is possible to see what's going on in boxes, microwave ovens, and larger structures like vehicles or aeroplanes, etc. But in addition to that, something which is quite unexpected is that if you take the power cord of the microwave oven, using a current probe, you can detect a lot of signals on the power cord which are seemingly getting out from the microwave oven. That's very interesting for us to note, because something which gets out of the microwave oven, which we can detect on a spectrum analyzer with frequency, tells us there's energy escaping. It doesn't escape at the microwave frequencies of 2.45 gigahertz, but it does escape at other frequencies like the power supply frequencies. And lo and behold, that energy goes down the power cord, connects to Earth. Where would Earth be? It's a plug in the wall, but that connects to some copper connection, maybe outside a house or a building. And what you'll find is that that energy always flows in circles, and the current gets back to the microwave oven using some kind of capacitive coupling, which you can't see. But the important thing is that if you move your microwave oven up or down, that current path changes according to your environment. And that's important because if I make a measurement of interference in a laboratory and I go somewhere else and the conditions of the Earth connection change, I will discover I get different results. So people won't agree with the measurements I made. So I just want you to be aware of the way in which one might think when looking at EMC, and getting into these field distributions and current distributions becomes quite important. Now in this particular picture here, you will see that there's a little waveguide in the microwave oven. There's a magnetron, which you generally can't see. That magnetron puts energy into the microwave oven. And if you visualize that waveguide as something which contains electric fields, using Maxwell's equations, the electric fields cause magnetic fields, which cause electric fields, which cause magnetic fields, and it propagates the energy into the oven. But in the process of producing a magnetic field, which you see here, which always circulate around the electric field, the magnetic fields are at right angles to the metal wall. And the right angles to the metal wall tells me I get a normal magnetic field and a current which flows at right angles, which shows me where the currents are going to flow, either on the box or the waveguide. And all of that is good to know. And as long as the path for the currents to flow is continuous, nothing gets into or gets out of the system. But if you put a slot in the system, like for example this lead connection, at the slot, what happens is the current tries to flow across the slot. It can't. It has to go around the slot very, very quickly. And in going around the slot very quickly, we accelerate charge, and this causes radiation, which is another topic which is important for us in EMC. Much more significantly in EMC is talking about systems which are connected by cables. What I would demonstrate through experiments or through more detailed material is that the moment you connect a cable to a system, that cable going down to ground, coming back via some undefined earth path, connecting back to the system, those current paths are determined by the shapes of your cables. And if, for example, I've got a system A, which is quite a big system, and nearby I've got another system with cables on it, those two loops will cause interference coupling between them. And you'll discover that some electronic activity in system A couples into system B. If you then try and save wires, and on an aircraft, for example, you've got maybe kilometers and kilometers of wiring systems, and you want to make the aircraft lighter, you might decide not to have 4 wires, as we have here, 1, 2, 3, 4. You might decide to only have 3, and you share a wire. And an experiment which we can do shows us the consequence of sharing wires. This system scales. This could be printed circuit board to printed circuit board. It could be small system to small system. This could also be a large utility network in a country coupling to a neighboring line in the same country. It all scales. Now, what are the practical implications of this? Let's just take a substation. This is a substation with a transformer and bushings. So on the right-hand top picture here is a picture of some real bushings. And on the right-hand picture, we put a very defined earth return path. And in the middle picture, we put a very vague dangling wire. And that gets illustrated by this schematic picture over here. In the dangling wire experiment here in the middle, you will find that you've got a measurement circuit with a coaxial cable. You've got a dangling earth reference. You've got a central bushing, and that forms a 3-wire experiment. Because the dangling wire is undefined, the coupling in that experiment or interference is quite bad. But if you define the loop using a very well-positioned earth strap, what you find is the coupling gets reduced, and it's always the same. It doesn't depend on what the measurement wire does, because I've now defined the first loop. And this becomes important for making very, very sensitive measurements. To bring the scale back down, this is an experiment where we take loop number 1 and loop number 2 and put it into a box. This is a metallic box. And we obviously get coupling between loop 1 and loop 2, and you can see it here in this computational analysis of the experiment. And the question here gets asked, is it better to stop the coupling from loop number 1 to loop number 2 using a whole box? Is it better using a circular metallic plate, a square plate, or a vertical plate? And what's quite fun, and I thank Ernst Berger from EMSS, now out there in South Africa, very close to Stellenbosch University, this is a picture of using a vertical plate where between the 2 loops, you put a vertical plate in, you ground the vertical plate, that kills the capacitive coupling dead, and by grounding the vertical plate, you also manage the currents and therefore the magnetic fields. And this is a simple way to stop coupling from system A to system B by just seeing where the currents and fields exist in the system. So to start bringing this to a closing point, this is an EMC cabinet principle. Here's a filter that all of us might want to put into a piece of electronics or a box that we create to stop energy getting onto our power cord. What this experiment here does is it takes a signal, it puts it through this filter, takes it out the other side and measures the response. So effectively, I'm measuring an input signal going through a filter, coming back out, and I compare the input and output signals and tell you how well this filter works. You will see I've got various connection options here, and in one of them, we just literally put the wire through a hole in the wall. If we do this, what happens is energy from the outside goes straight through the hole in the wall, goes onto this filter, and if I pick the filter up, that energy can go underneath the filter, go to this wire, go out through a hole in the wall and back to where it came without even going to the filter. Look, you're getting a clue that what I'm doing there is saying, if you don't visualize what your currents are doing, you can completely get rid of the properties of something you intend to have a purpose like filtering. What I do here is I use a current probe to measure the characteristics of the input signal. I either put in a capacitive barrier or I put a hole in the wall. And when I go through a capacitive barrier, the energy only goes through the capacitive barrier. Nothing from the outside world gets into the inside world except the current that I want. I properly ground the filter. The energy goes through the filter and the filter does a job of work. Just to indicate that what the currents do becomes important and how the field distribution exists is something I would look at. Piet van der Laan first pointed out to me that if you can measure 5 microamps of current on the outside world, or 14 dB microamps, that current, which could come from your inside box, if it gets to the outside world onto one of your cables, that current alone will hit the CISPA radiation limits for EMC. If that's the case, you might as well not even go for proper EMC testing if you know you've produced more current in the outside world than you should have. So one of the things I do in the laboratories is I always measure to see if my currents are below 14 dB microamps, and if they are, I can be relatively confident that I will pass a radiated test in an official laboratory measurement. To give an illustration of this, this is a box very like this, a bit bigger. Did an experiment done recently where we put a filter into the box, and the filter was put into the box where it was connecting to the aluminium box. And when we measured the radiation signals in a range of 30 megahertz to 1 gigahertz, we discovered a lot of energy in this area, which we could detect on the cable coming outside the box. And the question was why? When we looked into it, we put a current probe on the outside, we put a current probe on the inside, and discovered we measured the same currents on the inside and the outside of the box, which meant that the wall of the box was not isolating the currents and keeping it inside the box. That's because it was aluminium, it wasn't connected properly. Literally within 45 minutes, we took the same box, didn't change anything, we just made a better connection of the filter, and that alone caused a reduction of that signal by 20 dB. 20 dB is a factor of 10. That reduction of a factor of 10 is relatively easy to get in EMC. A factor of 100 or 40 dB is a bit more difficult, and a factor of 60 dB has to be done by design at the beginning. I've been showing you things on the scale of a microwave oven, on the scale of a box. This is a real processor bunker called the Karoo processor bunker in the Karoo of South Africa, and it's part of the Square Kilometre Array site where telescopes are being built to look back into the origins of our universe. And what I want to illustrate here, is that because of the experiments that I've just been describing to you, we persuaded the civil engineers to connect at a very regular spacing all the reinforcing wire which went into the concrete. This then turned this 50 by 50 meter system into a big box. We then made sure that all the power cords and all the signal cables going into this bunker went through a very, very well-defined interface plate with proper filters. And then we showed that nothing from the inside got to the outside. And here, inside of this processor bunker, we put all the cables into trenches, making sure they were defined, not going randomly all over the place, forming loops. And by so doing, we minimized the loops, we minimized coupling between the motors and the air conditioning units and the processing computers, and we stopped energy getting from the system out the processor area, over the hill, into our telescopes on the other side. So it works on that scale. And what I want to say is that the principles work on a small scale, go right up to scales like this, and up to national systems. Same principles apply. So what you've seen in the perspective that I've shown you are some of my thoughts and some of the EMC building blocks I've built up over the years. This was a journey which I was taken on when I didn't first understand EMC, but through people like Piet van der Laan, Lex van Dersen, Dave Geary, I've learned a great deal more, and through, of course, my own work. The key theme, as you saw, was to identify troublesome currents and manage them. The capacitive or electric field, very much like the rain you saw on that Dutch cartoon roof that I showed you to begin with, capacitive coupling, electric fields are easy to get rid of. You put metal plates, you ground them, and the problem is solved. EMC problems on any scale are solved with the same thinking. Whether it's large boxes, whether it's small microcircuits or printed circuit boards, we use the same thinking. This video technical note summarizes some of the approaches we use to support industry, and we've prepared this material as our contribution to demystifying EMC. We trust this helped. Let us know if it did. Goodbye.